Hi geographers, welcome to this lesson about the main landforms of coastal erosion. We're going to be considering a few things in this video. Firstly, the factors controlling erosion and thinking about the things that determine how quickly erosion happens on a coastline. We're going to be examining then the main landforms created by erosion, which include things like headlands and bays, cliffs and wave-cut platforms, and also then the erosional features that we find on a headland, things like caves, arches, stacks and stumps. If we start by considering the factors affecting erosion, you might want to just pause this video at this stage and just think to yourself, what are the main things that influence how quickly erosion might happen along a coastline? Okay, so if we examine some of these factors then, first and foremost, we need to consider the wave strength. That in itself is determined by factors like the fetch and the wind speed. So if we have high wind speeds or long fetches, then we're going to have more energy being transferred to the ocean, which is going to create larger and more powerful waves. And in turn, those powerful, destructive waves are going to have more erosive power, primarily because of their strong backwash. So the strength and type of wave that we have affecting a coastline at any one time is going to influence the rate of erosion. Linked with that is also what we refer to as the bathymetry, or the underwater topography of the ocean or seabed. That has an impact on waves depending on whether the seabed is gently sloping or quite steeply sloping. If the seabed is quite gently sloping, the waves will have friction with the seabed quite some distance from the shoreline. And what that means is as the waves enter that inshore zone, they're going to slow down, they're going to experience friction with the seabed, and they're going to lose some of that energy before they actually hit the coastline. If, on the other hand, the seabed is quite steeply sloping, then that's going to mean that the waves aren't going to expend much of their energy before they actually reach the shoreline, and therefore will have more energy to direct at the rocks in the form of erosion. Beaches are very important in determining the rate of erosion as well. If there are large beaches in front of cliffs, then those beaches are going to act as a natural shock absorber and absorb some of the wave energy before it reaches the shoreline. On the other hand, if we have areas where the beaches are very narrow, somewhere like perhaps the Holderness coast on the east coast of Yorkshire, it's a very rapidly eroding coastline, and that's because the beaches there are very narrow and they offer very little protection against the oncoming waves. Other features like headlands are also important in determining the rate of erosion. That's because of wave refraction that we've looked at previously. Headlands refract the waves and cause the erosive power to be directed at the headland, meaning that the waves in the bay either side of that headland actually have less power. Although weathering and erosion are different processes, weathering can actually complement erosion in terms of creating weaknesses within the rock, which can then be further exploited by the processes of erosion. So where weathering rates are higher or quicker, then the rates of erosion are also likely to be faster as well, because one speeds up the other. The final factor that has an influence on the speed of erosion is human activity, and this can be quite complex depending on what is actually happening. So in some cases, activities such as dredging, where we remove material from the seabed, that material would normally dissipate wave energy, so if we remove it, then that wave energy is going to be higher. Likewise for things like coastal management, if we install groins or seawalls in one location, while we might slow down the rate of erosion in that location, it's very likely that we would increase it elsewhere, particularly further downdrift along the coastline in other parts of the sediment cell. Those areas might experience greater rates of erosion because perhaps the transfer of sediment from one place to another isn't happening in the way that it normally might. So they're some of the main factors that influence the rate of erosion. I also want us now to have a little look at how the rocks are arranged along a coastline and how that can influence the rate of erosion. Just like you to take a look at these two different sections of coastline here. And again, maybe just pause the video and just have a think about what you notice about those two sections of coastline. Okay, so hopefully you've picked up that along this section of coastline, the layers of rock run parallel to the shoreline. Okay, whereas here, the layers of rock are running perpendicular to the shoreline. So in this location, we have one rock type exposed all the way along that stretch of coastline, whereas here, along this stretch of coastline, we have several different rock types exposed. Now we have names for these types of coastlines, and we call them concordant and discordant coastlines. Concordant coastlines are these ones here, where we have one rock type exposed parallel to the shoreline. The rock layers run parallel, and therefore only one type of rock is exposed to the sea at any one time. Particularly along this stretch of the coastline in Dorset, so areas around like Lulworth Cove or around Kimmeridge around here, those areas are very typical of concordant coastlines. They tend to be relatively straight because the rate of erosion is going to be quite similar because it's the same type of rock. However, we do find small coves or inlets, Lulworth Cove being a really good example of that along the Dorset coastline. Discordant coastlines, however, like the area around Swanage, is where we have several types of rock exposed at one time. Those rocks might vary in their hardness or their level of resistance to erosion, and therefore some might erode more quickly than others, and that leads to that classic formation of headlands and bays that we can see forming here around Swanage. So discordant coastlines, they occur where the layers of rock run perpendicular to the coastline or perpendicular to the shoreline. Again, here the rate of erosion is going to be more varied. It's less regular than it is on a concordant coastline. Moving on then, we can start to examine some of the landforms that are created by erosion. So one of those is the formation of a cove. Now a cove forms at a concordant coastline. So just like we can see in this set of diagrams on the left, the bands of rock or the layers of rock are running parallel to the shoreline. Each of these different colours on this diagram represents a different type of rock, and we can see that in the first step only one type of rock is exposed to the sea. Now generally what happens is perhaps that outer band of rock might be more resistant to erosion, but eventually it's going to be breached in some way. The waves are going to find a weakness or a way through that resistant rock, and that might be aided by the flow of a river into the sea. So we can also see on this diagram a little river flowing down into the ocean, and the river's created a little opening in that harder band of rock. And once the waves are able to break through that outer band of rock and maybe reach softer layers of rock behind, that rate of erosion actually increases. We can see that the erosion continues inland, but also that it spreads out laterally as well. It spreads out sideways as the waves are able to erode that rock into that very distinctive cove shape. Eventually what will happen is probably that erosion will continue until it reaches some harder rock behind. So in this case, this lighter coloured rock here might be a little bit harder, and therefore that rate of erosion is going to slow down or even stop. Again, forming that classic kind of cove shape, a narrow entrance to the cove here, and then that wide, almost circular shape to the cove here. Obviously, a really good example of that is Lulworth Cove, and we can see if we look at this photo and this map together how that translates to the diagrams that we've just been looking at. So in terms of the rock types along this stretch of the coastline, there's a very resistant band of Portland limestone which just sits on the edge of Lulworth Cove here. It's basically indicated by this section of the cove here. So this rock that we can see on the very edge of the shoreline, this is the Portland limestone. This is very resistant, but once the waves have broken through that, we can see how the wave action has been able to erode inland and how it's been able to erode laterally as well, again creating that kind of classic cove shape that we saw here. In relation to the rock types, This is where the waves have been eroding through the Purbeck limestones and the Wealden beds, and eventually what they've done, which you can see in the back of this photo here, they've reached that chalk rock at the back of the cove, and this is what started to slow the rate of erosion down. If we have a look at other areas on the map as well, we can see that places like Bacon Hole here or Stair Hole, they're very similar, but perhaps just earlier on in the formation of this landform. So we can think about Stair Hole and Bacon Hole perhaps being a little bit closer to kind of stage 1 or 2 in this process, whereas Lulworth Cove has very much reached the end of that formation. Similar to the formation of coves is the formation of headlands and bays. However, this time these landforms are found on discordant coastlines where we can see that at one time we've got different rock types exposed to the waves. So here we have 2 bands of chalk forming the headlands and a band of clay in the middle forming the bay. Perhaps what you could do at this stage is just pause the video and have a think about what annotations you might put onto this diagram to help you explain the formation of headlands and bays. Okay, so firstly we want to think about the importance of those different rock types. So in the case of the headland, that's been created because that more resistant rock, in this case the chalk, that chalk rock has been eroding but very, very slowly, and therefore this harder rock is left behind, sticking out to sea as a headland. The same applies on this side of the diagram as well. In the middle though, that softer rock, the clays, they've been eroded more quickly, and that rock, which may well have once been out here, has retreated back, creating that classic bay shape. So the differential rates of erosion here, the clay eroding more quickly than the chalk, that's responsible for the formation of the bay. A couple of other things that are important. We find a beach developing in that bay. That's because the headlands are helping to shelter the bay. They're offering some protection against some of the high energy waves that might be coming in. Therefore, those low energy waves in the bay, they're going to be depositing material. As well as that, as that bay has been formed and the rocks that were once part of this band of rock here, this clay rock, as they've been broken down by attrition, they are naturally also forming the material that becomes part of the beach. The final thing that's important in the formation of headlands and bays is the process of wave refraction. So once headlands and bays start to form and they become more pronounced, and you've got this headland and bay formation, wave refraction then happens. And if you're still a bit unfamiliar with that, go back and have a look at one of the previous videos about waves. But as the wave then approaches the coastline, it bends to mirror the shape of the headlands and bays, and what that does is concentrate the wave energy onto the headlands. So a wave approaching on either side of that headland would be concentrating its energy onto the headland, meaning that the waves in the bay are going to be less powerful, and that links with what we were saying earlier about those constructive or low energy waves in the bay. So again, that's further encouraging deposition and the development of the beach in the bay. Really good example of this locally in Dorset is obviously Swanage Bay. Swanage Bay itself is made of mudstone, and that's surrounded by 2 headlands. Durlston Head made of limestone and Ballard Point made of chalk. If we have a look on this map here of Swanage Bay, you can see that classic headland and bay formation where we've got one large headland here which consists of Ballard Point and an area known as the Foreland. And we've got another headland here which consists of Peveril Point and Durlston Head, and then we've got the bay in between. If we overlay the types of rock, again you can see a little bit more clearly how this bay has developed. So the limestone that we have down here and the chalk that we have up here, they formed the 2 bands of resistant rock which have created the headlands, and then the mudstones that are in the middle, sandwiched between the 2, they've retreated faster, again helping to form that classic bay shape that we find here. In this photo, again, you can see that classic shape of the coastline. This is Peveril Point that we can see in the far distance of the photo. So this is that limestone headland sticking out to sea. We can't see the other headland because it would be behind where this photo is being taken from. But you see that classic bay shape, and we can see the development of the beach there in the bay. So the third set of landforms that we'll look at are cliffs and wave-cut platforms. So where you have cliffs made of consolidated hard rocks, they tend to form wave-cut platforms in front of them. You can see on this diagram here how originally the cliff would have extended out here, but it has retreated over time, and it's left behind in front of it a wave-cut platform. Again, what I'd like you to do is just stop for a moment and have a think about what annotations you might put onto this diagram to explain the formation of this landform. Okay, so the first thing to consider with the formation of wave-cut platforms is where the wave energy is being concentrated. We can see we've got this arrow here which denotes where the wave energy is being concentrated at the base of the cliff. We have a name for this part of the cliff. We call this the wave attack zone. The wave attack zone is generally delimited or marked out between the high water mark, where the waves and water would reach at high tide, and the low water mark. So we can imagine here perhaps this is at low tide, and between high and low tide the water is going to rise and fall along this part of the coastline, and the waves are going to be concentrating their energy within that wave attack zone. What that does is create at the base of a cliff a little notch at the bottom, and we call this a wave cut notch. So let's add an annotation onto our diagram to explain that. So we could say that over time wave action is concentrated at the base of the cliff, forming a wave cut notch. So the waves have eroded that notch out of the cliff there. As well as that, subaerial processes are going to be acting on the top of the cliff, things like freeze-thaw weathering or carbonation, and that's going to be in turn weakening the structure of the rocks at the top of the cliff. So let's add that on as an annotation as well. Eventually, what will happen is that wave cut notch will increase in size until the top part of the cliff can't be supported anymore, and then that part of the cliff will collapse through some form of mass movement, most likely a rockfall or a landslide. So again, let's add that onto our diagram as well. As a result of the collapse of that cliff, it will expose a little bit more of the wave cut platform. So we can see originally when the cliff was here, only a short section of wave cut platform will have been exposed. As that repeated cycle of undercutting and collapse has happened, more and more of that wave cut platform has been exposed. It's also important for us to consider the role of the material that falls off the cliff and what that will mean for the wave cut platform itself. So if we imagine that when that cliff collapses, it's going to leave lots of debris in the sea. Large and small chunks of rock are going to fall off the cliff and they're going to end up in the sea. As well as those rocks perhaps being broken down by attrition and becoming smaller, they're also going to be dragged backwards and forwards by the waves. And as a result of that, there's going to be a lot of abrasion on the wave cut platform. That material that's fallen off the cliff is going to help to smooth that platform through that process of abrasion. So let's add that on as the final label to our diagram. The final thing to say about wave cut platforms is that as they get bigger, what they tend to do is actually slow the rate of erosion down, because as the waves are now approaching that cliff, they're going to be travelling over that wave cut platform and they're going to be experiencing some friction with it and therefore losing some of their energy before they actually reach the base of the cliff. So the larger the wave cut platform becomes, the slower the rate of erosion tends to be, because that wave cut platform is acting a little bit like a beach does to absorb some of that wave energy before the waves hit the base of the cliff. In terms of some good examples of these features, if we look locally in Dorset, the area around Kimmeridge has some really good examples of wave cut platforms. We can see here this photo is taken at low tide, where the tide's quite far out, and it's exposed this platform which actually surrounds either side of this little headland that sticks out here. So this is a feature known as Broad Bench, and this wave cut platform wraps actually all the way around this headland. At high tide, when the water level rises, the waves actually come up against the cliff edge here, but then expose that wave cut platform at low tide. And that's quite common with wave cut platforms. They tend to be hidden at high tide and then exposed when the tide goes out. We can see, although it's a little bit pitted with rock pools and things like that, it's generally quite a flat, quite a smooth surface because of the role of abrasion. A really big example here on the south coast of Wales in a place called Southerndown. We can see that huge wave cut platform extending all the way down to the sea down here. Again, this is taken at low tide, and as the tide rises, we can see that the water level would get up parallel with that cliff line there. You can start to understand here what I was talking about on the last slide with the role of wave cut platforms in absorbing wave energy. Now, as the waves travel over that wave cut platform before they get to the base of the cliff, they're going to actually be experiencing quite a lot of friction with the seabed and therefore losing some of their energy. Final set of landforms then is to consider the erosion that takes place on a headland, forming that classic sequence of landforms: caves, arches, stacks and stumps. Again, what I'd like you to do, pause the video at this stage, have a think about how you would annotate each part of that diagram to explain what's going on and why those processes are occurring. Okay, so if we start on the left hand side, we work our way through this sequence. First thing that happens is that there will be lines of weaknesses on that headland, which are going to be exploited by processes like hydraulic power or cavitation, and those cracks or weaknesses are going to be made larger, wider and taller. Eventually what might happen is that one of those cracks or weaknesses might also coincide with some weathering on top of the cliff, and actually the erosion might continue upwards, creating what we call a blowhole. This is where a crack or weakness or small cave at the base of the cliff actually has an opening in its roof, a little bit like a chimney actually. And what happens as the waves approach the headland and they crash into the base of the rocks, water that gets compressed into the crack or the weakness or the cave gets actually forced upwards up the blowhole and actually kind of spurts out the top. So on stormy days when that wave energy is quite high, lots of water can be forced into those blowholes with quite considerable force, and the water spurts out the top, just like we would see on the blowhole of a whale when it comes to the surface of the ocean and it blows the air out of its blowhole. It's the same kind of feature that we see along the coastline. Over time, as I said, those cracks and weaknesses are going to become larger, and the undercutting of the cliff is going to continue until we find a cave being formed, a large opening on the face of that headland. What we have to remember is that because this is a headland, the same thing could well be happening on the other side. So we might have a cave forming in a similar position on the other side of the headland, the side that we can't see in this diagram. We have to remember that wave refraction as well, causing the wave energy to concentrate itself on the side of the headland, isn't it? Eventually what will happen is those caves might meet, or certainly the cave is going to become larger and larger until it breaks through to the other side of the headland. When that happens, we're left with an arch, and obviously Dyrhólaey is a really classic example of where two caves have broken through the headland, creating that classic arch shape. Now, just like with cliffs and wave-cut platforms, we shouldn't overlook the role of sub-aerial weathering processes. So the top of that arch is going to be weakened through a number of processes, maybe freeze-thaw weathering or carbonation, until eventually the roof of the arch can't be supported anymore. It's not able to withstand the weight, and combination of all those processes are going to weaken it to the point where it collapses. What that will do is leave behind a stack, or a tall isolated column of rock gets left behind. That's what a stack is. Old Harry in Dorset, just on the headland to the north of Swanage, that's a great example of a sea stack. There are lots of others dotted around the UK's coastline as well. Eventually, what will happen to that stack is the wave energy at the base will cause it to topple over. So we can imagine that we'll get like a little wave cut notch forming here and a little wave cut notch forming here, and actually over time those notches will get bigger and bigger until eventually, just like if you were chopping a tree down and you chopped away with an axe at the base of that tree would fall over. Same thing happens with the stack. It gets weakened at the base and then the stack topples over and collapses, and you're left behind with a stump. So in some cases we actually see on a headland all of these stages in action. We can identify caves, arches, stacks and stumps on one headland, but we also have to remember that actually the same headland could move from being a cave to an arch to a stack to a stump over time. This is the headland to the north of Swanage, a place called the Foreland. We can see that chalk headland there, and in the foreground of that photo we can see this stack here. This is Old Harry rocks here. We can see a little stump next to it here. This is what was Old Harry's wife. There was another stack next to Old Harry, but unfortunately during a storm she collapsed over, so she is no more. Poor Old Harry. That was his wife there, and we can see in the background we can see another couple of stacks here off of those headlands. We can see some caves forming in the bottom of those cliffs. We can see those caves getting a little bit larger and possibly even forming an arch through to the other side of that headland there. And again, a very good location for us to consider the sequence of those landforms being developed here. A little bit further afield, because it's important that we have an awareness of coastal landscapes beyond the UK. This is a series of stacks on the coast of Australia known as the Seven Sisters, and in Iceland this is like the Icelandic equivalent of Dyrhólaey, a place called Dyrhólaey, literally means door hole island. And again in the middle of that photo there we can quite clearly see that classic archway. We can see a little stump here, we can see a stack here in the foreground as well, and in the background of that photo you can also see another little set of stacks there. So we find these landforms wherever we have headlands, and the wave energy is concentrating itself around those headlands as a result of wave refraction. So that brings us to the end of this video about erosional landforms. Make sure that you're happy with each of those landforms, as well as the factors that control the overall rates of erosion. Whenever it comes to explaining the formation of landforms, a couple of really good tips to remember. One of those is having nice clear sequences. So being able to sequentially write about how certain landforms are created in a nice logical, almost step-by-step process. And the other thing is using the correct terminology. So making reference to coastal processes, things like wave refraction, concordant and discordant coastlines. All of those things are really important in using that kind of terminology within your answers.